As I said last time, maybe the most important idea in all of Physics 2201 is the idea that force, some kind of a push or a pull, force is the thing that can cause acceleration. Force is the only thing that can cause acceleration. Whenever you observe an object accelerating, its velocity changing, you know that there are forces that are acting on that object, and it's those forces that are causing that acceleration. And Newton's first law of motion and Newton's second law of motion deal with that relationship between acceleration and force. Here's Newton's second law, and we can think of Newton's first law as really just a particular special case of Newton's second law. The second law tells us that if all the forces acting on some object, when you add them together, when you sum them all together to get the net force, the grand total force, if those forces don't all cancel each other out so that there is a non-zero net force, then non-zero net force means non-zero acceleration. Or to put it another way, if you see an object moving with constant velocity, in other words, the rate at which that velocity is changing is zero, no change in velocity. That means no acceleration. And if there is no acceleration, that's because the net force acting on the object must be zero. And it works the other way too. If you analyze the forces that are acting on an object, and if you find that all those forces add up to zero, then it must be the case that the object has zero acceleration. The object does not accelerate. So the logical implication works both ways. Zero acceleration implies that there must be zero net force acting on the object. And if you know that there's zero net force acting on the object, that implies that the acceleration must be zero. And similarly, if you observe an object and you see that it is accelerating, acceleration not equal to zero, then that implies that the net force on the object is not equal to zero. If you see an object accelerating, then you know that there must be some non-zero net force acting on the object. Right? Net force has to be non-zero in order for acceleration to be non-zero. That's what Newton's second law says. And similarly, if you analyze the forces on some object and you find that they add up to something that isn't zero, that implies that the object will accelerate. It'll have an acceleration not equal to zero. So that's the basic idea. A non-zero net force, all the forces acting on the object not canceling each other out, will always produce acceleration, some kind of a change in velocity. One other important thing that we see here in Newton's second law, on the left side of the equation is a vector. Acceleration is a vector, and the only thing that a vector can be equal to is some other vector. So this right-hand side here really is some kind of vector. And for two vectors to be equal, they have to have the same magnitude and they have to have the same direction. So the direction of this acceleration vector must be the same as the direction of this vector on the right-hand side, otherwise the two things cannot be equal. Well, the only thing here on the right-hand side that has any direction is the net force. So that means the direction of the acceleration must be must be the same as the direction of the net force, because otherwise the two vectors on the two sides of this equation could not be equal. So I've got that written down here. The direction of acceleration is the same as the direction of the net force, which should kind of make sense because net force is the cause Acceleration is the effect. The direction of the acceleration is the same as the direction of the net force because the net force caused that acceleration. Now, let's think not about directions, but about magnitudes, sizes here in Newton's second law. And we'll imagine that we're applying the same net force to a whole bunch of different masses, different objects with different masses. So then, if it's the same net force applied to different masses, then Newton's second law can be thought of, really should be thought of this way. Right? The magnitude, the size of the acceleration is just some constant number, the magnitude of the net force, divided by mass. That's an example of a very general, important kind of relationship where you've got two variables, y and x, and they're related in this case, in this way. One variable equals some constant factor divided by the other variable. So Newton's second law with constant net force is an example of this kind of relationship where the y would correspond to the acceleration and the x would correspond to the mass. This kind of a relationship between two variables is called inverse proportionality. We say that y is inversely proportional to x, or x is inversely proportional to y, and then we could write that relationship like this. Y is proportional to 1 over x. This symbol here means is proportional to. Y is proportional to the inverse of x. Or y is inversely proportional to x. Those things mean the same thing. So that's helpful when dealing with numbers, and helpful when trying to figure out how one factor, like mass, affects the other factor, acceleration. One thing you notice, of course, is that if x gets larger, y must get smaller. If x, in any time you've got inverse proportionality, when one variable gets larger, the other variable must get smaller. Right, if x gets larger, then the denominator of this fraction is getting larger, so the fraction itself is getting smaller, so y is getting smaller. Or vice versa. If we see that y is getting larger, that means that the other variable x must be getting smaller. Y is larger means this fraction is getting larger, and since the numerator is constant, this fraction getting larger gets larger because the denominator is getting smaller. Larger y means smaller x. Smaller y means larger x. That's how inverse proportionality works. But we can be even a little more precise, a little more quantitative than just saying that, than just saying in inverse proportionality, when one variable gets larger, the other one must get smaller. We can actually say how much larger, how much smaller. And the rule, the slogan for inverse proportionality that you should always keep in mind, and it'll make a lot of things easier if you do keep it in mind, the slogan for inverse proportionality looks like this. In inverse proportionality, if one variable changes by a factor n, that is, one variable changes by a factor of n means that the new changed value of that variable, let's say that the variable is x in this case, is just n times the old or original value of the variable before the change. So if one variable changes by a factor of n, factor just means multiplying, then the other variable, the variable that x is inversely proportional to, then the other variable changes by the inverse of that factor, 1 over n. That is, the new value of y is equal to a factor of 1 over n times the old value of y. I'll use subscript 1 for the old value before the change, subscript 2 for the new value after the change, always. So, for example, look at a Newton's second law case. Let's say you've got a constant net force applied to different masses, and let's say for one particular mass, that mass feels an acceleration of 2 meters per second per second. That is, in every second, and here we're really just worried about magnitudes of acceleration, not directions of acceleration. In every second, the velocity, or rather the magnitude of the velocity, the speed, changes by 2 meters per second in each second. So if the object is speeding up, then if the velocity is 1 meter per second at one point, then 1 second later, the velocity is 3 meters per second. Or if the object were slowing down, then and the velocity at one moment is 10 meters per second, then 1 second later, the velocity will have changed by 2 meters per second. The velocity will be 8 meters per second. So we know that the net force has that effect, creates that much acceleration for this much mass. But now let's say we try a different mass that's 4 times larger. The new mass is 4 times the old mass. In other words, the variable mass changes by a factor of 4, which means, go back to our slogan here, one of those inversely proportional variables, mass, has changed by a factor of 4. N is 4 in this particular case. That means the other inversely proportional variable, acceleration, changes by the inverse of that factor, 1 over 4. In other words, the new magnitude of acceleration is inverse of that factor times the old magnitude of acceleration. So that's 1/2 meter per second per second. It's accelerating only 1/4 as fast when the mass is 4 times greater. Now let's look at another example. Let's say a constant force is still being applied to a whole bunch of different masses. And one mass of 3 kilograms gets accelerated by that force so that the magnitude of its acceleration is just, well, some number we don't know what it is. But we do know that for a different mass, m2, the magnitude of the new acceleration is 6 times the magnitude of the old acceleration. So we apply that slogan again. One of the inversely proportional variables, acceleration, changed by a factor of 6. So the other inversely proportional variable must change by the inverse factor, 1 over 6, meaning the new mass is 1 over 6 times the old mass. In other words, the new mass is 3 kilograms divided by 6, or 1/2 a kilogram. Notice what happened here in these two examples. In this example, we had more mass, and it resulted in a smaller acceleration. In this example, the new mass was a decreased amount of mass, and that resulted in more acceleration, 6 times more acceleration. So that's always the way it's going to be, and you can see that just by looking at Newton's second law here. If net force is a constant, then greater mass always creates less acceleration. Smaller mass creates more acceleration. Right? Smaller mass means the denominator of this fraction is smaller, so the fraction itself is bigger. Less mass means more acceleration. More mass means less acceleration, and that actually tells us what mass means. Mass is our way of measuring something that we call inertia. Mass is the amount of an object's inertia. And inertia is a measure of how difficult it is to make the object accelerate. It's a measure of how strongly the object fights against being accelerated. Right? More mass, in other words, more inertia, means that for any particular amount of net force, that force creates less acceleration. Mass measures how strongly an object resists being accelerated. Mass measures how difficult it is to accelerate an object. More mass means it's tougher to accelerate, which means any particular amount of net force applied to that mass will produce less acceleration, and vice versa. Smaller mass means less difficulty in accelerating the object, so any particular amount of force would give you a bigger acceleration. That's what mass means. In the previous video, when I was talking about weight, the gravitational force from the Earth on an object, I mentioned that weight and mass are two very, very different things. Weight is a force. Mass is a way of measuring an object's ability to fight a force. Mass is a way of measuring an object's ability to resist being accelerated. In a sense, you could say that mass is kind of the opposite of a force. A force produces acceleration. Mass hinders the acceleration of an object.